welcoming everyone that is here to the 2022 Central Convergence Symposium. So for those of you that are across the country, we've heard many grandmas and grandpas being said hello to, as well as parents and teachers and friends. So with that, we want to start off by saying welcome, but also to give you an idea about what your students have been doing this summer. What is a summer REU? Well, the first thing it is research. So the Council of Undergraduate Research defines undergraduate research as an inquiry or an investigation conducted by an undergraduate student that makes an original intellectual or creative contribution to the discipline. And all the students are presenting today, you're going to see that all of them have done that this summer. And many of you thinking that your students did an REU in mathematics, research in mathematics, probably have these images in your mind. Whiteboards or chalkboards full of equations, little computer simulations, so many little pictures. And these are actual pictures from our experience. So this has definitely been part of it. But there's also so much more. In 2021, the REU last year, we had students provide one word to describe their experience. They said research is repetitive, conquered, frustrating. Research is breakthroughs, complex, awesome. Chasing your tail, feeling relief, feeling directionless, and clarifying. Okay, so that gives you a start. That's what we told our students initially. And then this year, they came back. And we gave them up to 5 words this year. And so we have perseverance in new directions, stressful, lots of writing, productive, straining, rewarding, informational, hard-fought progress, frustrating, some other word that I can't read that I totally wrote, hard-fought progress, headaches, coding sex, sorry, grandma, confusing, disappointment, then hopefulness, and work, right? So your students have done a lot of work this summer. But we've also had some fun. This is the 4th of July picnic. This is a puzzle. This is going to a baseball game. This is climbing a mountain. We've also had a large number of cats and dogs, even though we aren't no longer doing this virtually. People still wanted to make sure their cats and dogs were able to attend. So a lot of our presentations have ended with some form of pet. So we told our students at the beginning that there was going to be a lot of aspects to the research, a lot of more. But really overall, what I want you all to know is that our students have stuck with it this summer. And actually, we even created a slug award to recognize those people who slugged through every week. Students had to be nominated by other colleagues. This is not everyone that received the awards. I apologize, I couldn't find all the pictures today. But it was amazing to see how much our students were able to see in their colleagues the work that each other had done and really support each other back to back. So with that, I give you the 2022 CC-REU students. And I hope that you will work with me to welcome them as they are going to take and present their information. Our first presenters are going to be the hormone modeling team who worked with me. Our presenters will be Matthew Cowen, Noah Dalian, Felicia Persner, and Nate Wilson. So come on up.
Hi, Mom. Where's the clicker at? Doesn't get any better when you get up here. My heart is still racing. Yep. Alrighty, hello guys. Thank you for joining us today. Our group is modeling the PCOS or Polycystic Ovarian Syndrome, like I said, or like Dr. Brady said rather. Nolan, Matt, Nate, and Felicia. Let's get it kicked off. To start off, we're just going to give you a little outline of where exactly we're going to be going today. We're going to start off by talking about the menstrual cycle, as PCOS is a syndrome that directly affects the menstrual cycle. And then we'll talk a little bit about PCOS itself. We'll then go into some of the models that we use in modeling the menstrual cycle, and then end with the model that we made for PCOS and the model that we made for treatment for PCOS. And so to start off, let's talk a little bit about the menstrual cycle and what exactly it is and how PCOS affects it. And so the menstrual cycle has two main phases. The first of which is the follicular phase, which is on the right. At the beginning of the follicular phase, there's menstruation. And then throughout the follicular phase, that's when the follicles grow. And then at the end of the follicular phase is where ovulation occurs. And that's where the egg is released, going into the luteal phase. The follicle breaks down, turns into the corpus luteum, and then this cycle will restart and continue over and over again. In terms of some active hormones over the course of the menstrual cycle, two of the main hormones we look at are the follicle stimulating hormone, or FSH. It spikes 2 times throughout the menstrual cycle. The first is during the follicular phase, which promotes follicular growth. And then the second time is due to a spike in the luteinizing hormone, or LH, which happens right before ovulation, signaling the release of an egg.
So what we have here is how the brain connects to the ovaries. It starts in the hypothalamus, which sends out a GnRH pulse to the pituitary, which is also in the brain. Then the pituitary releases FSH and LH, which begins that cycle in the ovaries of follicle growth, scarring, and then forming the corpus luteum. During this cycle is when estrogen and progesterone are released, which can create a positive feedback loop back to the brain. This is the 2-gonadotropin hypothesis, which is what is occurring in the ovaries. We have the granulosa cell and the thecal cell. So it starts with the pituitary releasing FSH to the receptor on the granulosa cell, which stimulates estrogen to be produced, which then causes progesterone to go back to the brain and signal the pituitary to release LH. This binds with the receptor on the thecal cell, which produces testosterone, and testosterone will cross the membrane between these two cells, and testosterone will then be aromatized in the granulosa cell to be turned back into estrogen. And this creates a loop. So what we're talking about today is Polycystic Ovarian Syndrome, also known as PCOS. It's typically defined by the presence of ovarian cysts, but that's not always the case. There are many different symptoms that someone with PCOS may experience. This includes excess testosterone and also anovulatory infertility. This means that someone is infertile due to a lack of ovulation.
And next, we will be talking about modeling. So why do we want to use a mathematical model? Well, first of all, it allows for variable input into our model. So this allows us to really fine tune and tweak any parameters we'd like in order to create the best possible solution. Second of all, it provides a great visual representation of our problem. We use things like graphs and charts to be able to help us to understand the problem better. And lastly, it solves real-world problems incredibly accurately and efficiently with the use of modern computing.
So the first model that we use in modeling the menstrual cycle was the Chin and Ward model. And the Chin and Ward model consists of 3 differential equations that describe the masses of the follicle, rupturing follicle, and the corpus luteum throughout the menstrual cycle, and 5 auxiliary equations, which help describe the hormone concentrations of FSH, LH, GnRH, progesterone, and estrogen. So this image right here depicts the equations that we used in this model. And so the top 3 are differential equations, and the bottom 5 are the auxiliary equations. And while it might look intimidating, the main thing that you want to get out of this is that whatever we're subtracting off of one differential equation will then be added on to the next differential equation. And this concept will remain consistent throughout the remainder of our models. Taking a look at the success or lack thereof of the Chin-Ward model, it's pretty clear if you look at the FSH and the estrogen graphs here. Our model is the solid line, and the dots are data provided by McLaughlin et al. This model does not fit the data very well at all. But really, the whole purpose of this model is just to get an idea of how the differential equations are used. And so
using that Chin and Ward model for a little while, we realized it wasn't quite biologically accurate enough for us, which is why we decided to use the Hendricks model as the base for our PCOS model. And so the Hendricks model consists of a system of 16 delayed differential equations and 5 auxiliary equations. And like the Chin and Ward model, it does model the change in mass of follicle, the ruptured follicle, and corpus luteum, as well as the similar hormones. So here's the first set of equations that model the follicle growing during the menstrual cycle. So if you notice, that first equation is PRA1, and then on the image on the right side there, that first circle is going to be PRA1, and that is where the follicle begins to grow until we hit the RCF circle, which is where the follicle is going to rupture. Then after rupturing, it will turn into the corpus luteum at the CL1 and CL2 circles. And then after turning into corpus luteum, it will continue secreting hormones until loop 4, which is the end of the cycle. And here's the second set of equations, which models hormones in the brain during the menstrual cycle. So that equation 13 is going to be the inside of this diagram. That's going to start at the independent stage here. And as we keep going around there, we'll hit that FSH, the LH, and then the LH support phase to end the cycle. And additionally, here are the graphs for the Hendricks model. And as you can see, these curves fit the data points quite a bit better than the Chen and Ward model did, which again shows that better biological accuracy.
So now that we have a model, we really want to look at taking the menstrual cycle and turning it into a PCOS model. So how can we change the Hendricks model into a model that models something we would see in PCOS? So in our research, we looked at insulin resistance. And the reason we looked at insulin resistance is because we wanted to see levels of increased testosterone, which happen when we have insulin resistance, changes in weight, and also hair growth. So these are some of the things that we wanted to address. And when we were looking into insulin resistance, we noticed that during the luteal phase, progesterone strikes and insulin resistance is increased. So we can see that there's a lot of hormones in play when insulin is involved as well. So when we decided to model insulin, we couldn't find any real differential equation system. So in our model, we took data. And as you can see from this data from Meena Kumar et al., we have the follicular phase and the luteal phase. So all of the phases of the menstrual cycle are covered. We could take this and create a data set, and we could graph the said data set and create an interpolating polynomial that goes through them. This interpolating polynomial goes from 0 to 29 days and it has cyclic behavior. So it will, at 29, will reset and continue to do the same cycle continuously. Please go back. One thing I'd like you to notice is that in the control group, the levels are much lower than the PCOS group. So next we've got to figure out how we can implement this into the model. In comes the insulin ratio. So this insulin ratio is taking the control group and the PCOS group and basically making a ratio of the two so we can see how many times more there is insulin in a person with PCOS rather than somebody in the control group.
So our PCOS model is building upon the Hendricks model that we spoke about earlier. We've incorporated insulin into the differential equations and the auxiliary equations and changed 7 of the parameters in order to better fit the PCOS menstrual cycle. So what we'll expect to see with this increase in insulin is an increase in the GnRH pulse, which leads to an increase in LH and a similar level in FSH, which then leads to a decrease in estrogen, a decrease in progesterone, and an increase in testosterone, which ties back into the two-gonadotropin hypothesis I spoke about earlier. So here we have the testosterone equation from the Hendricks model. What we see when we increase insulin is that there's an increase in testosterone. So we increase that testosterone parameter, which then causes a waterfall effect of other parameters that need to be changed in the original Hendricks model, which is how our PCOS model was built. Here we have the original parameters and that testosterone equation from Hendricks again. So what we did to change these equations is that we multiply the testosterone parameter by the insulin ratio and also by a new parameter to get to our desired testosterone level for PCOS, which is much higher than in the original menstrual cycle. So here are these changes. We see an increased level of LH, an increase in testosterone, decrease in estrogen and progesterone, and similar levels in FSH. The shift in the graph is due to the cycle length being shorter for our model, but this is still biologically accurate as someone may have a shorter cycle or a longer cycle. So we can continue with our model.
And lastly, we will talk about treatments for PCOS and how they affected our model. So the treatment on the left, birth control, is the most popular one right now. This helps you rebalance hormones as well as clear any acne and excess hair growth, and also helps prevent pregnancy. The one on the right is less common, is metformin, but this is the one we actually decided to use in our model because one, it lowers the insulin and androgen levels, which is something we were looking for, as well as causing ovulation to happen so the person who has PCOS can become fertile again. And we'll now show how we incorporated metformin and the results it gave us.
So when incorporating metformin, we got to come back to this idea of the insulin ratio, which is something that's going to need to change. As I talked about earlier, the insulin ratio in somebody with PCOS is much higher. So what we ended up doing was creating an equation, and in the insulin ratio, we implemented metformin into the PCOS, which we'd end up lowering the insulin ratio or the insulin in somebody with PCOS. So as you can see, if metformin equals 0, we're still floating around that 2 to 2.5 range of multiple. And then in the metformin equals 15, we can see that it goes all the way down to 1 to 1 or around there. Obviously, it's not perfect because insulin ratios will never be 1 to 1 with somebody with PCOS. Next thing we have to focus on is the parameters that we added. And if we just left them in here, when we increase metformin, the original parameter won't come back when we increase the metformin. So as you can see here, when metformin equals 0, we have exponent that makes it so that the parameter is the same when metformin is 0. But as you can see, as we increase through, when metformin equals 15, we get the parameter equaling 1. So we can see how this looks in equation by pulling up the testosterone equation. And if metformin equals 15, which means we're bringing it down to a 1-to-1 ratio of insulin, you can see that the insulin ratio goes to 1 and the parameter also goes to 1, therefore leaving us with the original Hendricks model.
And with all of this incorporated into our model, this right here shows what the graphs would look like with metformin equal to 0. And what we would expect to see is that these equations look identical to the previous insulin PCOS model. And that's exactly what we see here. Because basically what this says is that if you're not being treated with metformin and you have PCOS, I mean, you have the insulin model, right? But if you have metformin equal to 5, 10, or 15 in terms of how effective it is at bringing the insulin levels down, that's what these graphs show right here. And again, what we would expect to see is if we say that metformin has the effectiveness that we would like to see, it's going to bring the model back to what, like Nolan said, the Hendricks model. And while we don't necessarily see that it brings it back exactly, that's what we expect because the insulin ratio is never exactly 1-to-1 at any point in your model.
And then here, I'll just go over a few future improvements we'd like to make to our model. The first one being to figure out more optimal parameter changes and then go ahead and implement those. We'd also like to build a system of differential equations to model insulin. Right now, the insulin ratio we're using isn't quite as biologically accurate as we would like it to be. So we'd take that new insulin model in and go ahead and replace the insulin ratio with that. We'd also like to incorporate more symptoms and treatments of PCOS, as well as getting better data, because the better data really drives a better model. And here are references. Thank you very much.
We needed
Everyone got muted just now.
Oh, okay. So the question was, how did we pick this this research topic and why were we on this avenue? And so the answer to that question was that previous people did this research, although they ended up doing something different where they combined the Chen and Ward model and the Hendricks model to make a new set of differential equations. We ended up wanting to do something where we could implement some sort of treatment. So we ended up making a problem in a PCOS model and then implementing it.
I would like to add that there is a lack of PCOS research, and there was not a PCOS model created beforehand. So this was us creating a PCOS model and then implementing treatment.
So I'm assuming you weren't biology majors, since you're in math REU. Are there some challenges in modeling a phenomenon that you may not be as familiar with, and how do you address those challenges?
Yeah, that's a great question. And let me tell you, there's a lot more reading you do in a math REU than you'd expect. Especially in the Hendricks paper, I read that the first time through and I was like, okay, I understand the math of this. And then coming back around and trying to implement insulin, I was like, wait, what does this parameter do again? So you have to go back through and understand the actual biological aspects of it before you can really say, okay, this is something that I can change. So yeah, there is a really big biology thing. less biology professors who upload videos to YouTube. But yeah, it was a real struggle, but something that I think we overcame, and we learned a lot of biology through this.
I want to offer, if anyone online had a question, we could, or a compliment, we could take them from chat.
Okay, 4 people showed up since the last one.
Well, do you want to do that?
Love you guys.
Okay, well,
So let's thank our speakers one more time. And then
Should we fix something or?
But we did get
From Dr. Bisgard. The differential equations variance of a tank mixing problem. So
this is Dr. Bisgard trying to be funny because he knows that I really, really love tank mixing problems because they do a really good job of explaining what is happening in the system of differential equations. And at the beginning of this REU, I did try to explain the differential equations through a tank mixing problem. So thank you. Wait, Anisha, no, I'm just kidding. Thank you.
Okay, thank you for your patience. Welcome. I'm Matthew.
I'm
Brendan, Dennis, Ariana. Yeah. And over the summer, we've studied prospect theory and applied it to a study on mouse tracking and gambling. So every day we face numerous challenges for which we make decisions and have to operate in some way to get the best optimal outcomes. These can include, what should I eat for breakfast? I'm playing a game of chess. What move should I make if I want to beat my opponent? Or, more complicated, if I have a 50-50 gamble where I can earn $100, should I take that? Or should I take $30 for certain? Bit of a harder question. This is the one we focus on though. Yes, we'll be focusing on this one. But first, some guiding questions for our presentation was, can we model individual decision-making behavior, and then how does risk factor into that decision-making behavior? Right there.
So first, to introduce our topic, we have to go into defining what utility theory is. So utility theory, which was developed approximately 100 years ago, is a mathematical model of essentially happiness. Utility is defined as being a measurement of satisfaction or happiness. The mathematical model itself is the function, a utility function, which is assigned to show the usefulness of a change in happiness. In our gambling situation, the utility function is representative of the satisfaction that you could gain or lose. And while it may seem that for a dollar amount, which is what we're looking at, the utility function equal to X is a reasonable utility function, most utility functions in real life actually demonstrate diminishing marginal utility. So what that is, for example, if you open a bag of chips and you eat 10 potato chips, those first 10 are going to feel very, very nice. However, once you eat 100 of them and you eat 10 more, they're going to feel probably good, but probably not nearly as good as the first 10 when you open that bag and you have that amazing smell. So this could be mathematically represented with a power function here with the exponent between 0 and 1. And lastly, since we'll be looking at gambles, we mathematically represent the utility of a gamble as the probability times the gain and the probability times the loss. It is half here for both of these since it's a 50-50 gamble. And now some developments of utility theory eventually led to the theory of prospects. So under prospect theory, gains and losses are weighed separately. So for example, a person might weigh losing $1 the same as gaining 2. And empirically, it's been shown that this is a recurring behavior with many different individuals. So mathematically, Cowen and Tversky, the two developers, created this model. So in this utility function, we have X denoting the value, the dollar value that we're looking at, and we have alpha and beta being the diminishing marginal utility for gains and losses separately. Gains are the top part, which is greater than 0, and losses, which is less than 0. And lastly, the key factor is lambda, loss aversion. Essentially, lambda has been shown to be greater than 1 as people value losses more than gains.
In 2020, Stillman, Crosby, and Ferguson made a study on how people to see how they would react to different gambles that they were presented. A total of 3 studies were conducted with a total of 652 participants. Each participant faced 215 gambles. 165 were mixed gambles, such as you could either gain $5 or lose $3 with 50-50 chance, or you could just pass and take $0. And then the other 50 gambles were gain-only gambles, where you could say gain $5 or gain nothing with a 50-50 chance, or you can gain $3 for certain. In the third study, Stillman et al. Introduced the concept of risk manipulation, where participants were asked to think of the gambles collectively, like a stockbroker, like this is only one of many gambles where one loss won't be that bad, or to think of the gambles individually, where like you'd have a much more risk aversion. So in the mouse tracking that Stillman et al. Collected, we collected the following parameters, including area under the curve, maximum deviation, reaction time, and our own that we calculated from the trajectories, the minimum opposing distance. So we'll see a visualization of those parameters for area under the curve. You can imagine this as, imagine a straight line from the start to the finish, and then you got the trajectory, and then the area under the curve is the area between those two curves. Next, the maximum deviation. You still have that straight line from start to finish, and this time you're looking at the greatest distance at any point to the straight line. And then finally, the minimum opposing distance is the smallest distance you can have to the choice you did not choose.
So looking at the correlations between these variables, first we looked at MOD and MD, and as we expected, the correlation was very high, as essentially these two are opposites. According to Pearson correlation, it is a negative 0.97 relationship with statistical significance. However, we were surprised that the correlation between area under the curve and maximum deviation was high. As a result, the correlations between all 3 of these variables, AC, MD, and MOD, were all very high. However, correlation between reaction time and the other variables was found to be weakly correlated.
So here are some sample trajectories of people that took a bit more of an irregular path with our mouse trajectory thing, a bit different than the previous examples you gave. So you can see part of the reason we looked a bit more into maximum deviation and mod is the area under the curve for these 2 trajectories is a little bit complicated. So to go through the framework that Stillman, Krajcik, and Ferguson used, they originally had this utility function with the same marginal utility for gains and losses, rho. And then we have our choice function, probability to accept, and our log likelihood. My colleagues will talk more about these individually.
So the utility function given by Stillman et al. Is basically almost like Kahneman-Tversky's utility function, except alpha and beta have the same parameter. So like Kahneman-Tversky's utility function, X is the value of the gambles, such as gaining $5 or losing $5. Rho is the diminishing marginal utility. So like the greater rho is, the less likely you are to be like valued like more, less, I guess. But like if you have a smaller value of rho, you're more likely to like lose interest in like say greater gambles really quickly. And then finally, lambda's loss aversion, which this is before, is like the greater lambda is, the more likely you are to hate losing. So. And then in the previous research from Stillman et al., Stillman showed that a high area of the curve was correlated to a high perception of conflict. So like, for example, if you have 2 gambles that are really close to each other, you're not sure whether to take it or not, then that would indicate with a high area of the curve. Next, Stillman used what's called a bootstrapping method to analyze his data. So basically what that means is you optimize all of the parameters alpha, beta, and lambda, and you use that on all of the parameters, and you use the optimal parameters and go back and predict whether they take each gamble or not. So that's basically you're using all the data, getting some parameters, and then analyzing it on the data again. And finally, our own research improved the original framework that Stillman had, and we had better results overall.
So with our framework that was previously talked about, we now have the only change here is in our utility function at the top there, where we are now having a difference with alpha and beta.
Okay, yeah, by simply changing alpha and beta so that they might be different for each participant, well, that gives us a better model. And it ended up being the case that this made our model a little bit better. But what does one of these look like? we go to the next slide. We plot out a couple prospect functions for one individual once we optimize the parameters. As you can see, this is a prospect function, but we can now answer questions like if you had a gamble to say that this participant was facing a gamble of $2 that they could win 50-50 or losing that same $2. How do we apply that? If we go to $2 here and look at the y-axis utility here, this is pretty large. It's larger than the difference from here to here for -2. So this participant is likely to take that gamble to a -2. On the other hand, we looked at and do that same analysis here with a different participant. We have a little less than 2 utility here, a lot lower -2 utility here. So this participant is likely to pass.
We also looked at choice functions. So a choice function is a function that represents how likely a person would choose to gamble. So there are a lot of different choice functions that are available. We use the one that Stillman et al. Used, which is a logic function with the new parameter mu. So what mu represents here is that a higher mu would represent a more consistent choice, or rather a more consistent method of choosing when to gamble, while a lower mu would represent more inconsistency. And it's mathematically represented like this. And some examples of that. So this first example, we're looking at subject 124 from study 2. Their mu was approximately 3. So what this represents, if you look at the bottom left, since this is equal to the probability of accepting a gamble, you can see that around here, if the difference of utility is between -0.5 and -1, it's kind of fuzzy. They're not likely to take it, but they could. And the same idea is represented between 0.5 and 1 here. On the other hand, with a higher mu, as shown with this subject, it's very obvious to tell when they're likely to accept. There's a small region around 0 that's always a very strange area, since that's if we compare 0 passing it and the others, then there's a lot more confusion there. But it's much steeper, so it's a more consistent method of choosing. So for optimization, we noticed that the choice to gamble is binomial, which is represented like this, with P as probability accept. And then we repeat it for all trials. So we just multiply all the binomial probability distributions together for one individual. So then what we do is we optimize this. What we do in optimizing that, we look at this negative logarithm function, and we minimize it for one individual to get the parameters for each individual.
So here are some histograms that describe the distributions of the alpha, beta, lambda, mu parameters for each one. We have a little bit of a normal-ish distribution right here around 1, and we've got some spike behavior for the rest of them. Of note is the low beta behavior at 20. We had to put in we had to do some limiting. We bounded the parameters because we ended up getting some really bizarre outliers at a couple points. Yeah.
So you might ask yourself, what is the relationship between these parameters? So as you can see here, we have alpha v lambda on the left, and you can see there's this almost straight line that exists, but this kind of weird patch in between alpha 1 and alpha 1.5, where we have the lambda values ranging all the way from 0 and all the way up to above 10. So this kind of indicates that these are not highly correlated enough to consider them to lump them together. And this is more of made of a point with alpha and beta, and the reason that we continued with our 4-parameter model. While this could fit per chance a linear line, it is not highly correlated enough to consider those to be the same, which is why we found an improvement.
So we can use the p-accept that we used before in order to determine whether a participant took a gamble or not. So we calculate p-accept using the optimal parameters, and we use that to determine whether it's greater than or equal to 50% or less than 50%. So if it's greater than or equal to 50%, we predict that the participant takes the gamble. Otherwise, we don't think it does. And we use the bootstrap analysis as before, using parameters alpha, beta, lambda, and mu. And then some of our results that we obtained. So with Stillman's original 3-parameter model, about 87.5% of all gambles were correctly predicted across all 3 studies, whereas with the 4-parameter model, about 88% of all trials were correctly predicted. This is a slight improvement, but we figured we could do a little bit better. So in order to do that, we decided to look at one of the parameters, maximum deviation, and you can see that it has a bimodal distribution roughly. So over here, you can see that there's a peak over here, and then over here, you see 2 peaks. Those peaks are basically the same absolute values, so we consider them essentially the same. And then we use a cutoff about right here, which if they're below this cutoff, they're more decisive and their maximum deviation is a lot smaller. Whereas if it's in this region over here on the right, the maximum deviation is larger, so they're less decisive. So we can use that to compartmentalize the data.
Okay, so then what we did is that we divided the data into two different subsets for the decisive region and for the indecisive region using the maximum deviation data at the cutoff point of 0.3. So this is one example of the alpha that we did, and then we repeated this for beta, lambda, and mu. So we found the parameters of all these from optimizing the data within these two different regions.
So by having this cutoff point of 0.3 and dividing the data, we can see without the cutoff point, we have this, and on our horizontal axis here, this is our predicted number of gambles. So the model that we are predicting versus the actual number of gambles taken. If we wanted a perfect prediction, that would be a straight linear line from this diagonal here. So our model on the right here, by dividing from this cutoff and optimizing those subsets from the decisive and indecisive region, ends up being slightly more linear and getting us to a 90% level of prediction. So to conclude, we first did this 4-parameter model where we were able to see a 0.69 level of improvement, but from then implementing this maximum deviation and creating two subsets and optimizing from those, we were able to improve it by a whole 3%. So we can now see what is really helpful with trying to make a model of prediction and potentially carrying that to future research. So future research, we might want to look at more of these mass tracking parameters, reaction time or minimum opposing distance, but also incorporating this mass tracking data to create more subsets. So finding that cutoff point for all of those other variables and seeing how that can improve our model. We want to modify our choice equation. So you saw with our framework, we only really edited the utility equation there, but with our probability to accept, if we use a new framework for that, we could further improve our model. And then eventually providing a split test analysis where we use most of the data to train it and then use that to test it on the other.
Here are our citations, and thank you so much for listening.
Now open to any questions section.
You're getting claps.
From the chat.
I think that was a while ago, but yep.
That was earlier.
Yeah, it was from a while ago. So.
Okay. But if you click on the participant,
I mean, why would we?
There's two claps.
yeah,
Oh, it's a clap feature. Okay. There's chat.
Thank you.
There's okay.
All right, are there any questions from the audience? Yes, Dr. Levy.
You answered most of the questions that came up during the talk later in the talk, which was great. Have you tried any cluster analysis yet? Do you use all 4 of your variables to see if people's like alpha and betas and lambdas fit into groups?
Yeah, we haven't gone there quite yet, but what we plan to do a little bit later is, with the 2-parameter model with the maximum deviation cutoff, to plot 2 different values of alpha, 2 different values of beta, lambda, and mu, and see how those distributions compare to the originals ones you had before. So I think kind of basing it off that cutoff we had earlier would be a good idea.
Thanks, Dad. It's your mom.
Why or how did we choose this model?
Oh, okay.
That's a long one, but like basically, we started off our REU experience by looking at a bunch of these coding models. So these included like multi-attribute utility theory or like maximum utility theory. So we looked at a whole bunch of utility models, and then we found one like eventually like as a research project that looked interesting from our advisor who suggested it to us. And we thought this would be a good one to look more in depth. So,
and to add a little bit more on, yeah, we went through a lot of different frameworks to work on, but we ended up looking at this one because we wanted to work with data and look at like empirical studies. And a lot of the latest research into how people make decisions is using prospect theory. And there's a lot of previous research that this paper cited that use prospect theory and work with it.
Yeah, so this specific project allowed us to kind of apply the utility theory framework that we had already built up through the course of the summer onto this large data set with all these columns that hadn't really been utilized in the original model. So it allowed us to kind of patch that gap and explore in that respect.
Thank our speakers one more time.
I don't know if you love me now.
Yes.
How you doing?
Okay, how are you?
Stressed, tired, excited.
I'm
feeling a lot of
excited
things
for
right
Mm. So for those of you that can't see, we have to wait for something to get installed. So give us just a moment. We apologize.
Keys work or just? Yeah, I think the mouse definitely works. The keys doing something, then they work. It's awesome.
What's our utility for using the keyboard?
Very small, but only one person can hear it.
Are we happy?
Yep.
Okay, but then I need to, I'm gonna come back and do Control L in a second. First, I need to do this, and then I need to do this, and then I need to that, there. We good?
Does the clicker work? Or the mouse?
No.
Our next presenters are doing variations of the Duchy's four-number game. And our presenters are Kieran.
It's not a good look, Dr. Brady.
Anish, Mason, Tasha. Okay, let's try this one again. And so our next presenters are the Duchy's four-number game. This are variations of Duchy's four-number game. Our presenters are Kieran, Anish, Mason, and Tasha. I'm gonna go sit down.
So that's a good idea. All right, so Duchy's four-number game, what the heck is that? It's a pretty elementary game. You start off with just a square and you put numbers at the corners, and then you take the absolute value of the difference of each corner, put that in the midpoint, and you have a new square. Keep playing that game until all of your numbers are 0, and depending on how many iterations that takes, when it reaches 0, that's the end of the game, and that's our length. For our first variation of the game, we thought, well, what happens if after each iteration, after each time you take a difference, you randomize the order of the numbers? So what's happening here is we start off 1, 2, 3, 4 again. And so we have our 3, 1, 1, 1 as our difference. And then we change the order on the left branch to 1, 3, 1, 1. And we keep the same one on the other side. And we just see if that exhibits any novel behavior. We want to see if it changes any of the behaviors from the base game. It turns out that we have non-zero convergence instead of just zero convergence. So our game will end with numbers that aren't just 0. And it's not always nice. Most of our games end up looking something like this, which is a little bit monstrous and it's hard to predict our behavior. But what's really interesting about this is almost all of the branches end in non-zero convergence instead of zero convergence. Why? How does that work? Why does it do that? So we go back to some of the key observations in the base game. And one of those is that after the 4th iteration, all of our numbers are going to be even. We use that in addition to another observation to prove that for every integer 4 tuple, you're going to end up with 0 convergence. So why is it different in this variation of the game? And so we're just going to check each one of the 6 unique parity cases to see if it has different behavior. A and E here end up being all even pretty quickly. So does D and E. B and C are a little bit different though. For case B, you have a 50% chance of being all even at the 3rd iteration.
but a 50% chance of converging to an odd, even parity. And for case C is really unique because it will always be odd, even parity. And so looking at that specific case and checking the first 3,136 four tuples, we don't have a single pathway in any one of those where we have zero convergence. And looking at that reason for that, it turns out pretty clear. If you have odd, even parity, there's no way for all of those numbers to be equal. So there's no way for all of the differences to be zero. What's also interesting is, at least for the first trillion possible values, all of our non-zero convergence is either in the form 0AA0 or 0A2AA. And there isn't any counterexample that we found so far. We haven't shown this analytically yet, but it's up to a trillion values. So it's safe to assume that we're going to see that behavior pretty commonly. The next thing that we did is we just looked at how many times will it always go to non-zero convergence? How many times will it never go to zero convergence for each of the different parity cases? And so on average, 60% of the time, you have always non-zero convergence. 0.4% of the time is always zero convergence, and 35% of the time, you have a 50% chance of going either way. So overwhelmingly, we have non-zero convergence. It's also interesting that if you have opposing parity cases, their distribution is exactly the same. And I'll let Nish go on his next one.
Hey everyone. So let's try playing the four number game one more time with initial values 12, 3, 5, and 4. After one iteration, we get a new set of values. But notice that there's an error on the right side of the square. 5 minus 3 is equal to 2, not 3. So for this variation of the game, when will we still end up with all zeros? In order to understand or answer this question, we need to analyze three parameters. First, how big is the mutation, aka how big is the error? For the purposes of this presentation, we're going to assume that the error is just 1. Next, on which side of the square does this mutation occur in? Again, to keep the game fair, we're going to assume that this is random, meaning that there's a 25% chance per side per iteration for the mutation to occur. Finally, when or how often does this mutation occur? That is, does the mutation occur every iteration, every 2 iterations, every 10 iterations, and how does that impact our game? And this is a little bit more complicated. But it turns out that the game never converges when there's a mutation every 1, 2, 3, or 4 iterations. On the other hand, the game always converges when there's a mutation every 5 or more iterations. But is this really the only way of thinking about there being a mutation in our number game? Or are there any other ways to do it? This is where we introduce the probability P of there being a mutation every iteration. So for example, if P is 0.5, then there's a 50% chance that there's a mutation every iteration. With the introduction of this P, how do our early results change, and what roles do the size of the error, aka the mutation value, and P have in this specific scenario? Well, it turns out that the game always converges, meaning it always comes down to all zeros if P is less than 1. That is, if the probability is less than 100%. So instead of focusing on when will it converge, we can now focus on how fast this will happen. In order to do this, let's first take a look at a graph of a bunch of simulations for P equals 0.5. That is, there's a 50% chance of a mutation every single iteration. So what this graph pretty much says is that, let's, for example, take a random X value, 50, and look at its corresponding Y value, which is around 75. It just says that out of all the simulations we've run, 75 of those games ended exactly in 50 iterations. And it's also interesting to note that this graph follows a very exponential decay-like format. So it's very natural to try to find its half-life. The half-life in a more biological context refers to the amount of time it takes for a population to die by 50%. But in this specific situation, the half-life refers to the number of iterations it takes for 50% of the games to die or end. So with the half-life, we can now use this as a characteristic to determine what roles the mutation value or the size of error and probability P play in our game. So first, let's take a look at the size of error. So as you can see, it's a graph for a constant P value of 0.3. And we see how half-life depends on various different sizes of errors. As you can see, this follows a very clear straight line. And so we can naturally assume that this is a uniform distribution. And so it's safe to say that the size of error actually does not play a role in determining the half-life, meaning it does not actually play a role in the entire game. However, this is very different for P. For a constant size of error 1, we can see that this graph is not a uniform distribution at all. It is more of an exponential curve. So it's very safe to say that the probability of the mutation plays a very vital role in determining the half-life, meaning it's very vital in determining the game's behavior. Now on to the next variation of the 4-number game with Mason.
Hello, so for my variation, I looked at what happens if instead of finding the difference between two corners, we add them up and reduce modulo m. The goal from the beginning for me was to find a basis for these cycles, and hopefully that basis could explain some of the weird phenomena we saw. So as an example here in mod 5, we start with 1402 on the squares. The image above is represented by the cycle below. We see by going through this process 4 times, we're back to where we started, which means that this is an example of a 4 cycle. Unlike Anisha's game, there's only a finite number of configurations possible. So that means that our game cannot go on forever. It eventually must enter a cycle. But that doesn't mean every configuration has to be part of a cycle. You can see here 0286 in mod 12 starts and it enters a cycle, but that cycle does not contain it. We can also add cycles. If we add entry by entry and reduce modulo m, if we do that to 2 n cycles, we'll also get another n cycle in that modulo. For those who have studied abstract algebra, that means we have a group under cyclic addition. Important thing to note here is some of the subgroup structure here. So if x is a n cycle in mod m, then k times x will be an n cycle in mod k times m. So here we see a 4 cycle in mod 5. We multiply everything by 2, we'll get a 4 cycle in mod 10. Multiply everything by 4, we'll get a cycle in mod 20. By 6, a cycle in mod 30. And for those of you who know group theory, this is just because the underlying subgroups are isomorphic. Something very interesting is that a configuration that belongs in a subgroup of even order, so there's an even amount of elements in it, cannot be in a cycle and will have to fall into a subgroup of odd order group for its cycles. So in our example in mod 12, you can see 0286 falls in the subgroup of size 6. And it's only when it reaches 0088 that it begins a cycle, because 048 is a subgroup of size 3, which is odd. Now, sometimes there are no subgroups of odd size except for the trivial subgroup 0. That's the case where the modulo is a power of 2. And in that case, everything converges to 0. So it turns out not just all of the entries can be part of an even size subgroup, but they individually cannot generate an even size subgroup. This symbol here means the subgroup, the size of the subgroup generated by A, that cannot be even. It also turns out that the determinant of a configuration cannot be even as well. I haven't defined the determinant yet, but the determinant is B minus A or C minus D mod M, which are both equivalent. As an example, in this 10 cycle, 2 minus 8 is -6, 8 minus 4 is 4, -6 and 4 are the same in mod 10. So that's the determinant. So we can actually use this to build a basis. So all of the cycles beginning with 00AA, 0AA0, or AA00, where A does not generate a even size subgroup, will form our basis. So if we take a general configuration of a cycle, ABCD, we can split it up into AA00 and 00DD, because we both know that A and D have this property. And so does the determinant, which allows us to add these 3 back up to ABCD. As an example, here's our 4 cycle in mod 5, starts with 1402. So we got our 3 bases cycles, 1100, 0022, and then the determinant 0330. When we add those will all cycle, they will all be 4 cycles, and when we add them back up, we get exactly what we had. So this will act as our basis. Things get a little bit different in multiplication, and for that, Tasha is going to tell us about it.
All right, so what I'm doing is very similar, except I'm doing multiplication instead of addition. So we still take the midpoints, multiply it. So a couple definitions first. A trivial cycle, because this will exist in all multiplication things, will always have 0, 0, 0, and 1, 1, 1. So we really want to focus on all the other ones. And then the other really important one is the constant cycle, which just means every element of it is the same. And we'll also need this function called the lambda function, which its value isn't really important. As long as you just take any value to the power of lambda, you'll get 1 in that modulus. And the last definition needs a theorem to motivate it, because if we have something in a cycle, you can see that 4 steps later, they'll all be a product of everything in it. So either everything shares a factor with the modulus or none of them do. So then we can divide it up into coprime cycles and non-coprime, where coprimes don't share any factor. And we'll first be looking at the coprime cycles. So first of all, we could do something very similar, where if lambda event is not a power of 2, we can actually generate a non-trivial coprime cycle, which is seen here. And this also has a really nice form because 2 steps later, with shifting everything around, we get the same thing, but it's squared. And because that's such a nice property, we will call these generator cycles. Because we actually can form a different basis, where out of just constant and generator cycles. And you can see in this example where this is a cycle modulo 7, that we can break it down into in a similar way, but we have each one individually is really nice to work with. So what happens if they don't exist? Well, that also only happens if lambda is a power of 2. So we got an if and only if there. So next thing I want to do is we can actually generalize this a little bit, because both Mason and my work is just a special case of working with abelian groups, which is just a set of things with some notion of multiplication between them, and just has all the notions of multiplication that you kind of want. And we'll also need the exponent in the group, where if you multiply a number by itself so many times, we'll eventually get back to 1. Or you can, and you just say exponents infinity. So for example, the integers with addition in Mason's case has an exponent of n. The coprime integers on n with multiplication have an exponent of lambda of n. So we can actually generalize to just repeating this operation in a general group, and then it will just go to a trivial cycle if and only if the exponent is not a power of 2. Additionally, we can, the basis I've shown for the coprime cycles also works for the general case. And I'm going to skip this next bit because we are running low on time. Bring this, so then the bit I was skipped is on the non-coprime cycles, but we'll get that just they exist if only if n is not a power prime. So bring that all together, we only have a cycle if n is 3, 5, 17, 257, 65,537, or a power of 2. And we also know how long it will take for things to reach a trivial cycle in those cases. And yeah, thank you for coming.
Any questions?
Oh, also the end of that statement was on the title side that was skipped.
Awesome. Awesome.
Matt?
Yeah, so I was wondering if you could talk about some of the similarity differences.
Yeah, oh, sorry. That's actually really interesting. In my paper, I'm actually going to talk about playing the game with direct elements of direct products of Z mod M, which acts basically the same. And a very important theorem, shout out to my professor, Professor Holdner, is a fundamental theorem of finitely generated abelian groups, which says that which gives us that all finite abelian groups are isomorphic to some direct products of ZM. So basically, that means that all finite abelian groups are isomorphic to the addition game that we've played. And not only follows what Tasha and I both found, that if the order is a power of 2, it can have trivial cycles. But furthermore, what I found is that if the elements are part of an even subgroup itself, they also can't be a trivial subgroup. So it's important to note that the addition game is not a specific case of abelian groups, but it represents all finite abelian groups via the fundamental theorem of finitely generated abelian groups. The multiplication game is so different because Z mod M under multiplication is not an abelian group. It's not a group. Z mod P is not a group. Only the group of units under multiplication is a group. And when you play that with, as Tasha did with coprime cycles, that's isomorphic to the addition game, so it follows the same structure as far as no even size subgroups can generate cycles.
Although I'm not only working with finite abelian groups, just groups with finite exponents, which is still a bit more general. In which cases, I still think it's easier to think of them as two different things that just have very similar properties.
I was trying to get there. Floop, floop. There we go. Why does the game always converge if mutation occurs more iterations apart? Is there a simple explanation?
So that's a good question. So to put it as simple as possible, an interesting thing about the original number game is the fact that after any 4 iterations, the last, the 4 numbers that you get are always even. And so there was a theorem that I came up with, was for the number game in general, with or without mutation, you can divide by a positive rational number and still get the same amount of end results as you would have before you divided it. And so when we have all even numbers, when we divide the entire set of 4 numbers by 2, we limit the maximum of those 4 numbers. And if we keep doing that over and over again, then the maximum has to be 0, which means all 4 numbers are 0. And the reason why we can say that, I don't know, there will always be 4 even numbers is the fact that since there's a mutation every 5 or more iterations, there will be a constant set of 4 iterations existing without a mutation in it. And so there will definitively have to be even valued numbers in that little group. Yes.
I don't mean for this to be long-winded, but if all of you could talk about if you had the ability to do future research on this topic, where you see your specific questions go.
So for me specifically, it's not related to the mutation in general, but just more of the idea that if you consider the set of 4 values as vectors and maybe doing the actual iteration as a matrix, as a transformation you're applying to that vector, thinking about what are the possible set of matrices in general, not just the Ducci's 4 number game, but just any set of matrices that could possibly have a result of, regardless of what the initial set of values are, it'll always end up getting to the 0 vector, something like that.
I want to know why the non-zero convergence are in such specific forms. Is there a way to show that analytically? Is there a counterexample? I'm also curious to see if the statistical chance of reaching a certain number or length of game is going to be the same as the base game, or if it's radically different. And if it is different, is there a way that I can show a relationship?
Like I said, I'm very happy with my results pertaining all the finite abelian groups. I would like to investigate what happens when we go outside of those groups, like in the case of multiplication, when we have cycles of 0 divisors.
I actually have a slide for future work.
How do we go back to it?
Share screen.
Or just share screen button?
Yeah. Bloop, bloop. It's there, I'm sure. Bloop. How about that? We're just making the chat bigger. Doop. Okay. Wait, Control L.
All right. So one thing that I found experimentally is, I'm going to move that chat, is also trying to factor the non-coprime cycles. And I've been working on doing this experimentally, that like we can still factor it for all moduli less than 153. And I've also looked into trying to do the games on, like, let's say 5 numbers or 65,536 numbers. Because it turns out that I have done work on what happens if the number of numbers isn't a power of 2. However, when it is a power of 2, there's still a lot more things that can be done.
We think our speakers. What I would really like us to do, we're gonna see if I can make this work.
I think we might have one more question if we have time for it.
Okay.
Do you have a question?
Well, I don't have a question. I'd like to make a comment.
Okay.
I started my mathematics education in universities 71 years ago. I'm really impressed about how more advanced you are now than I was when I was an undergraduate in mathematics.
Thank you.
It's really fantastic.
Thank you. Thank you so much.
Thank you so much. Okay. What I would like to do, I want to just try this, is have our students stand up and look at that lovely camera right there and just wave at all the people that showed up for you today. So I love the fact that we've been back in person. It's, I think, been really energizing this summer, but I also love the fact that we learned how to be able to do this virtually. And so once again, here was all of our presentations today. Anish, I apologize. I looked at you and thought about the slides you presented on the very first day, how you had like this great family picture and this picture of your sister. And then I couldn't remember, I was like, but, and then I thought about Rubik's Cubes and that was all I could think of. I could not think of your name at all. I just kept thinking, and how on that picture, you didn't actually have a mask. So I had seen your face. I really apologize. So I do apologize, Anish. That was all that I kept thinking of. So our whole entire group says thank you. Some of them started the summer with more facial hair than they had today. And we just really want to thank the people that came to support us and see us, because I think it made the presentations that much better. So thank you once again.
Great job, thanks.
Way to go, Matthew Helmer.
And I'm going to save the chat so you can get those comments from your. Okay, group. We got 1, 2, 3, 4. Is everybody still here? Okay. I am gonna turn this off.
Bye.
Bye.